network. Yeah. Okay, good morning, everyone. I hope you're ready for the last day of the week. Are you still sleeping a bit? Or... Okay, so this second session for PARI GP will be advanced algebraic number theory. So that will mean Galois theory and class field theory. Okay, so the principle is the same as yesterday. You can still go to this webpage for the PARI session, and you have the slides here and the plain text code here that you can copy paste into GP. Okay. Yeah, so Galois theory, bit of verification theory, and class field theory. Right. So, okay, quick reminder. So, yeah, we won't worry about separability here. Our fields will be either characteristic 0 or finite, so no separability problems. So consider finite extension of fields. We'll say that this extension is Galois if the bottom is exactly the field at the top, take the fixed points under the automorphisms. There's always an inclusion, but if you have equality, that's a Galois extension. And when that's the case, we give another name to this automorphism group, that's the Galois group. Okay? In this case, there's an inclusion reversing bijection between intermediate fields between these two and the subgroups of G, given by take the fixed fields in one direction and take the automorphism, fixing your field in the other direction. Yeah, everyone okay with Galois theory?
G is the Galois group.
Yes, sorry, yeah, that should have been Galois K or thank you. Yes, G is Galois. Okay, so now if you start, yeah, this is an important point that is sometimes confusing about Galois theory. If you start from one, let's say, irreducible polynomial that defines a finite extension, and that's not always Galois. Then there's a unique smallest extension on top, which is in fact Galois. That is called the Galois closure. And another way to see it, it's the splitting field of the polynomial, meaning the smallest extension that contains all the roots of the polynomial, over which the polynomial splits completely into linear factors. And then what we often call the Galois group of F, and sometimes we even say the Galois group of K, but that's an abuse of terminology, is in fact the Galois group of the Galois closure, which could be much, much bigger. Okay? And these Galois groups, so remember that's all, so now the polynomial F splits into linear factors in this K tilde. So this Galois group here permutes these roots. And very often we see the Galois group as a permutation group acting on this set of roots. So typically, you don't want to see Galois groups just as abstract groups, but as permutation groups. Okay? All good for everyone? Yeah? Okay. So now let's go to PARI, the PARI functionalities for this. So again, there's these two settings. You want the Galois group of the Galois closure, or you want the Galois group, but it's really the automorphism group of the field you're considering. So let's start with the first one. So we can compute the Galois group of the Galois closure of a polynomial or of a number field as a transitive permutation group. So this is so doing this in complete generality requires a lot of group theory, which we don't have in PARI. So there are some pre-computations that we store. And this is why we have the restrictions on the degrees to which this can apply. So by default, up to degree 7. If you download an extra package, you can go to higher degree. Maybe we could extend that if we do, yeah, if you download more pre-computation, you could extend degrees. Okay, so let's do this. You start with a polynomial and you ask for the Galois group of this. Well, probably you could compute it by hand in this case. But anyway, this is just to show the functionalities. and it returns to you a vector with some data. So let's look at what is in there. The first is the do I have the new Galois format on or off? Maybe I will have to check that. If you get one of these answers, if you get something different from what I get, we need to check something about the configuration. Okay, so this the group has order 8. And this -1 here is the signature. It's telling you whether the Galois group is contained in the alternating group or not. So -1 here, I mean, it's not. It's not contained in A4. So we say it has signature -1. This one here is just the an extra number to removing ambiguity after this information. So it's it's the first group of order 8 in the small groups database. This is there's a standard numbering of small groups, so that gives you which group it is. And there's a string that allows you to just parse that instead of using these numbers. Just read the string. Okay. So D4 is the group of order 8.
This is the gap and magma the small groups is the same in every system.
Yeah, right. Bill, we took care, like the numbering of small groups, it's the same as the small groups in GAP and the small groups in magma.
If you set default the new Galois format.
Yeah, there is a setting that needs to be correctly set.
Yeah.
Called new Galois format, because there used to be a different numbering and we fixed it.
Yeah, so this is the only group numbering. But you can get the gap numbering if you.
Which is probably a good idea, right? We should use the. Maybe we should put that in the.
I think Karim should have done something because he added this default, but then he never get around to change it. Because of course we would break
the default value. Yeah, the default value. Yeah, so.
Of course, you should never break Gonzaga program, so.
Yeah, so if sometimes you get not the same number as me here, it's probably you should set this default like this.
But at least in the new version, you get the name of the group, so at least you know what you are doing again.
Okay, let's do a couple more. This other degree 4 polynomial we have for that Galois group now is as order 12. It is contained in the alternating group. So now, well, you know what it is because it has order 12, and so it's A4. And another one, now the Galois group has order 24. Again, you know what it is, it's S4. Okay, is it working for everyone? This, yeah. Okay, so now, so that's for Galois groups as permutation groups. So this, yes.
When the Galois group as a group,
yes.
Kind of like reasonable way in numbering groups, or it's completely.
Yeah, it's that's something we would like to change at some point, but at the moment you don't know. You don't know how it acts on the roots.
No, you only know the isomorphism.
You know apt conjugation.
Yeah, exactly.
Yes, exactly. Yeah.
But there are other functions differently that.
Yeah, but this is a part of the functionalities that we'd like to improve at some point to have an actual permutation group with the actual action on the roots. Yes.
Do you have a permutation group without the action in PARI?
No.
No.
This is part of the project, part of the things we'd like to improve now. Okay, so the second construction, natural construction, is to construct the splitting field. So remember, this is the same as the Galois closure. So you start from your polynomial or a number field, either. And you can ask for the splitting field of that. So remember, the first one had Galois group D4, so it's degree 8, and the splitting field, and then here is degree 12. And I think I'm doing the third one probably. Yeah. And this degree 24. So as you can see, of course, when you do that, you tends to blow up a bit, right? So this is one place where it's often useful to use Polar best to get a slightly nicer polynomial for defining the field, because splitting naturally blows up coefficients a bit. So for instance, this is the third one. So you see, look like this. You get this fairly nicer polynomial. I mean, still, of course, it's degree 24. So how good can it be? But is working for everyone? Yep. Okay, so what can you then do? So what PARI is really good at doing is computing the automorphism group of a field that is Galois over Q. But this is so really it's for a field that's actually Galois. Okay, so this is done with the function Galois init. So you write like this Galois init. So remember, this is the PARI style initialization functions, just some prefix and init for it will compute some structure with some pre-computed data. So in particular, you have the gen components, which will give you a list of generators of this automorphism group, expressed as permutations of the roots. And here it's possible to know which roots it is. It chooses some p-adic completion and it computes the roots in there. There are some restrictions on the Galois group, which if you started from a smaller field and you took the splitting field, you can bypass that, but I think I'm not going to go into these details. But yeah, so Galois init, to initialize this, you can get the generators of the group. And then there's a bit more information. You can ask for, there's an orders component that gives you basically some orders that appear in some filtration of the group. So what this means is the order of the Galois group is actually the product of these numbers. Okay. I should have used vec here. Okay, anyway. Yeah, so this was the example where the Galois group was S4, so we recovered that. And we can also recover the gap index of the group here with Galois identify. You give it this structure, and it will give you a number, and this way you can recover the group in gap with this number, or in gap, or in my map, I guess.
It's without the name.
Yes, this one is, but I think we have, there's another function for the name, Bill. Mm-hmm. There's another function that will give you the name, right? Isn't it? Galois get name, yes, I think it's, I'm not sure if I. Oops.
So we got fully acknowledge the help of the GAP project for providing name to groups. I mean, it's not obvious at all what the name of a group is.
That captures D8, unfortunately, for D4.
Does it? Yeah. Yes. Actually, I also say D8 for the group of order 8. Yeah. I also usually use this, but like.
No, but I mean, there is different notation for transitive group and abstract group.
Yeah.
You have D parenthesis 4 and D subscribe 8.
Yes.
Error opening Galois file.
Yeah, this is
you're missing a package.
Okay.
If you have installed
yes.
Because we name an extra package called Galois.
Because
we should have checked that when we did the install party. We didn't check the
package. It is
package.
installed in the issue normally.
But It's not an extra package?
It is extra package, but the installation manual tells you to install all the extra package.
Yeah, but we didn't check that everyone had done it. We could have checked in the install session. Okay. Yeah, so you need an extra package. Okay, so once you have this, what you would like to do is, well, effective Galois theory. I mean, this is the point. Having this bijection between subgroups and fixed fields. So you can use the function Galois subgroups to compute the list of all subgroups of your group. So in this case, you can do that and you get the list of all subgroups. Okay, and yeah, I'm not describing how these subgroups are described. Maybe I mean, okay, look at the doc if you want to know a bit more about how they are actually described. But then, so we can compute fixed fields of various subgroups with Galois fixed fields. So you Galois fixed fields, you give this Galois init structure, some subgroup from this list, and you get some polynomial defining the subfield. Here I'm taking the first component because it also computes how this field is embedded in your big field. It's not just an abstract field; it's also embedded in your big one. And we can check that it's correct. Well, okay, we could look. I didn't look at its degree, but we should have the right degree compared. That should be the index of the subgroup in the big group. And here I'm computing its Galois group, which is now S4, but acting on 6 elements. So there's it's S4 as an abstract group, but as a permutation group, it's not acting on 4 elements. And in particular, it's contained in A6, which it wouldn't be on 4 elements. I'm doing another example here. So we take another subgroup, and yeah, actually, I'm giving the numbers in the list. Bill, is it like the ordering in which the subgroups is given? This is deterministic, right? Will they always get this? Do you get the same as me here? Yeah. Yeah, this is not the best way of setting up the example. So what we will get here is another copy of S4 inside of S6, which is not conjugate to the other one. That's why they have slightly different names. And in fact, this one is contained in the alternating group, and this one isn't.
In your slides, this new color format is off, right?
But I don't remember. Maybe I'm not sure because do you have different numbers here?
Yeah, 5.
Yeah. Okay. So probably I had. Yeah. I should fix.
700.
Yeah. Yeah. I should put the ones with the new Galois format. I did these. The examples are examples I've prepared a long time ago.
You should change it at some point.
I should change it. Yes. Yes. Absolutely. Yeah. Yeah, so
the whole Galois format.
Yeah, so the recommended version is this, which is not what's on my slides. Okay, any questions about computing Galois groups and effective Galois theory? Yes.
For p-adic fields.
For p-adic fields, no, there's no such. We don't have that for p-adic fields. For p-adic fields, I mean, currently we don't have p-adic fields in PARI. This is a project we want to work on with Billy, but so in particular we don't have their Galois groups either. Yes.
How are you supposed to put this command?
This one? You type exactly what I typed here.
No, there is underscore. You forget the underscore.
Where?
New underscore Galois underscore format.
Oh, it's new underscore Galois format. I'm sorry. Like this.
If you
Apologies.
actually mark, yes. No, it's okay. That's good.
It's not super good. Yeah.
New underscore Galois underscore format.
You see, Bill, maybe you should have done this one. Okay, so let's move on to a bit of ramification theory. So this was not part of the preliminary things I asked you to read. So maybe some of you know that already, some of you maybe don't. So, but I'm just going to give you some kind of crash course on this if you don't know ramification theory. So ramification theory is an interaction between Galois theory and algebraic number theory. It's like how Galois groups behave with respect to prime ideals, basically. Okay. So we start with the Galois extension of number fields with the Galois group G, and then we take some prime ideal of the top field. Yeah. Now we can define various subgroups of the Galois group. The first one is called the decomposition group. It's just the set of Galois elements that stabilize the prime ideal. Okay, so the prime ideals above a given rational prime are permuted by the Galois group, or above, in fact, the prime of f. Yeah, they are permuted by the Galois group. If you take the stabilizer, that's called the decomposition group. And it's and there will be numberings, and it's the number -1 in the number. So in particular, because it stabilizes this prime ideal, it also stabilizes all its powers, and so it acts on the corresponding residue ring. You get automorphisms of these residue rings. Yeah. And now you can define for each I non-negative the higher ramification groups. So the ith one is the one that acts trivially mod p to the I plus 1. Okay, so the one of index 0, it's called the inertia group. That's the one that acts trivially just on the residue field, and then you get higher and higher ones. And so this gives you a decreasing sequence of subgroup of the Galois group, and it eventually stabilizes to the trivial subgroup. Okay. There's a lot more to be said about this, but I will just stick to the definitions. Okay, another interesting construction is the following. So you have your residue fields that have an action of the decomposition group by automorphisms. So it's a finite field with an action with an automorphism group. Well, you know what the automorphism group of a finite field is. It's powers of the Frobenius map. And in fact, this Frobenius map lifts to an element of the Galois group on top. Yeah. And so there's always, so what is he saying is that this decomposition group surjects on the automorphism group of the field at the bottom. Yeah. And so this lift, we call that a Frobenius element. So here, okay, I'm assuming that it's unramified, otherwise you still have, sorry?
We can discuss.
Sure. Yes, so precisely here, I'm going to take, so start with the prime ideal of the bottom field, and you take a prime on top, hey, that above it. We'll assume that we're in the unramified case. This is really just for simplification. You can do something similar if it's ramified. And then there exists a special element of the Galois group, which from P, and that acts like the Frobenius element of the residue field. And if you vary the prime on top, that will change the Frobenius elements, but it will just conjugate it, and it will span a conjugacy class inside of your Galois group. Yeah? So this gives you, so you can think either as you range through prime ideals of the big field, it will give you elements of the Galois group. If you think of the prime below inside of F, it will give you conjugacy classes in the Galois group. Yeah? Okay, so let's see how to compute all of these explicitly. So earlier, like yesterday, we saw algebraic number theory properties like ideals, etc. That was with NF in it to compute ring of integers, prime ideals, etc. Then today we first saw how to compute the automorphism group that was independent of this algebraic number theory. Now we need to mix the two, so we need both the Galois initialization and the algebraic number theory initialization. So we compute the NF init of the field to compute the ring of integers and the discriminant, be able to work with ideals. And just to look at which primes are ramified, we'll factor the discriminant. Take a look at that. So yeah, remember factorizations in PARI, two columns. First one is the irreducible whatever, and second is exponents. So here the discriminant is 3 to the 28, 11 times 11 to the 16. So the ramified primes are 3 and 11. So that if we want interesting ramification groups, we should do at those primes. If we want Frobenius elements, we should do away from those primes. Okay. So let's construct some prime ideals. We do that as like yesterday with ideal prime deck. So we decompose 3, for instance, here. So we know that's going to be ramified because it divides the discriminant. And so we get 4 prime ideals above 3. They have residue degree 1, and they have ramification index 6. We knew that had to be greater than 1. Yes. Is it implemented, Bill? I mean, Frobenius elements for ramified primes. Is it implemented?
Okay. You can compute
because the prime at ramified primes, it's not a well-defined conjugacy class. It's only well-defined modulo the inertia group.
You should compute
but we could.
You should compute the ramification groups, and then you can get that.
But
this PARI has a function.
Yes.
So it is for all the primes, right?
Yes. We do RTNL functions, so yeah, so somewhere we must compute Frobenius elements also at the ramified primes, right?
Yeah, but
what
you should do is to compute the ramification group. Yeah,
but she also wants the Frobenius elements module in the quotient decomposition mod inertia.
It will be the generator.
Well, which generator? There are several generators, and only one is the Frobenius. And you must compute it because you compute the RTNL functions. So
it doesn't depend on which one it should.
It does.
Okay, maybe.
So okay? I think it's not exposed in GP. Maybe we should take a look at this.
Yes.
Have you tried asking? Okay, maybe we can take a look later. But I think currently in GP you can compute Frobenius elements only at unramified primes. I think. But maybe we should, I think internally it's possible inside the library, but
as far as concerned, it's not a Frobenius element. By definition, a Frobenius element requires that it's not ramified. It's something else.
Anyway, let's discuss this later. Okay, so we've got this prime, and now we can ask for the sequence of ramification groups. So we do that with the function ideal prime group. So now you need to give the NF structure for the algebraic number theory, the Galois structure, and the prime, and it will return to you a list of subgroups of the Galois group, indexed like I said, but the indexing starts at 1. So the first one is the one that I indexed -1, and then the second is the one that is indexed 0, etc. Okay. So in this case, so it stops when it becomes trivial. So you know that after the end of this list, it's just a trivial group. So here there are 3 interesting ramification groups. So the first one is again the decomposition group. We can identify what that is. It's 6-1. Yeah, I'm just showing you one extra function. Galois is abelian for a group. That's convenience. It's not abelian. Order 6. So this is S3 inside of our Galois group, which was S4. Okay. So the decomposition group is S3. And then we can take a look at the second one in the list, which is going to be the inertia group. And here it's in fact the same. It's also S3. Actually, well, if you know a bit of ramification theory, you know that because the residue degree was 1, it had to be the case that the decomposition group and the inertia group were the same. And the next one, so is the wild inertia group. In fact, we know that it has prime power order. So in this case, yeah, it's actually order 3. And all the next ones are just trivial. Okay. All good for this, everyone? Yeah. It's also working on your versions. Yeah. Okay, let's do the other ramified prime. So same procedure, we construct the prime. It has, so there are 4 primes above 11. They have residue degree 2 and ramification index 3. Again, we compute the ramification groups. There are only 2 that are non-trivial. 11 cannot be wildly ramified because it doesn't divide the degree of the extension. So there's just decomposition group followed by inertia group. And again, we can take a look at what is the first one. So decomposition group is again S3, and the inertia group is C3. Yeah, and here we knew that the index had to be 2 because that's the residue degree. Yeah, this one is okay also for everyone. Yeah. Okay, so at an unramified prime, we can compute Frobenius, the Frobenius element with ideal Frobenius. So let's do, for instance, at 2. So we decompose 2 to get prime ideals. So there are 6 prime ideals above 2. They have residue degree 4, and I mean, we know because it doesn't divide the discriminant, it has ramification index 1. It's not ramified. That's all good. And then we can use ideal Frobenius, again, NF structure, Galois structure, prime ideal. And that gives you some permutation. And this permutation is an element of the Galois group, and it is the Frobenius element. So here, for instance, we can ask for the order of this permutation with per order of this Frobenius. And it tells us that it has order 4. This is correct because 4 is also the residue degree. Okay. So yeah, I think ideal Frobenius will reject ramified primes.
Yeah. But there is a function, ideal of prime Frobenius in C.
Yes.
But you have to give it the ramification group.
Yeah, of course. I mean, but we could have a function that could put both at the same time. But yes, you need, of course, it's only well defined at the inertia.
Yes,
so
sure.
Yeah.
Why need to compute twice the ramification?
But we could export it in GP and it would be natural, yes. Okay, any questions about ramification theory? All good? Yeah. Okay. So third part, class field theory. Yeah, I think there was maybe a crash course in the notes I asked you to read as preliminaries, but I'm also going to give you some reminders. So there are 2 ways of expressing class field theory. There's the classical version, like pre-Adels, and there is the modern version, like more Adels, cohomology groups, etc. The classical version is more suitable to for computations because everything is expressed in terms of finite terms, so things that you can actually represent in a computer. So that's the formulation we use, but you can translate between the 2 if you need. So how does it go? You start with a modulus in a number field. That's just a convenient definition, meaning there's a finite part which is a non-zero ideal, and there's an infinite part, which is just a set of real embeddings of the field. And then you define some subgroup of K star. So that's the set of elements that are congruent to one mod your M, but what does it really mean? It's not, these elements are not necessarily integral, just means that the beta minus one has valuation at least that of the ideal at those primes, but it doesn't have to have valuation, positive valuation at other primes. Okay. And it needs to be positive at the place, at the real places you selected. Yeah? And now from this you can define the Ray class group, which is the quotient of non-zero fractional ideals co-prime to your modulus, modulo principal ideals with a generator that satisfies these conditions. Okay, so this is an extension of the class group, so it's also a finite ability. Everyone okay with this definition? Now, what does class field theory tell you? Well, for every modulus, there exists a unique extension of K called the Ray class field, so notation K of M, satisfying, well, the Galois group of this extension is canonically isomorphic to the Ray class group of that modulus. And in fact, so, well, if you just say that, this is not unique, but one way of saying, characterizing it uniquely is to say that you take a prime ideal co-prime to the modulus, it splits completely in this field if and only if its class in the class group is trivial. More precisely, the Frobenius elements in this class group correspond to just the class of the corresponding prime here. So there's a special case which is for the one of the usual class group, so that's trivial modulus, and it has a special name. It's called the Hilbert class field. Just a special case. So that's the first part of class field theory, and the second part is every abelian extension is in fact contained in a field of this form. So every abelian extension is contained in some Ray class group, and in particular by Galois theory, it means you can describe it by a subgroup of the Ray class group. It's going to be the fixed field under some subgroup of the Ray class group. If you're not very familiar with class field theory, maybe this is a nice example to have in mind. The Ray class groups of Q are simply the cyclotomic fields. Very nice extensions. Okay? All good with this? Yeah. Okay. So let's start with the simple case over Q. So then in this case, class field theory has another name because it was proved before. It's called the Kronecker-Weber theorem. And so in this case, we can apply special methods to compute abelian extensions. So it's with all subcyclo, meaning subfields of the cyclotomic fields. So you start with some, well, modulus, which is here just like number, which cyclotomic field you're going to look at. And you can ask for pulse subcyclo of this number and the degree you want, and it will give you the list of all subfields of the cyclotomic fields Q zeta n of degree 3. So yeah, do this. Okay, what did I? Yeah, here, okay, I selected, yeah, this is an occasionally to show you this GP syntax, which I'm not sure if did you talk about it in your preliminary? Have you seen this syntax before? No, okay. So this is the PARI syntax to mean, okay, I've got a vector here, a list of things, and I want the set of P, where P ranges over elements of this list, such that some condition is satisfied. So this is the syntax. Element, height, this is supposed to be like the belongs to sign in sort of easy characters, and then comma, and then the condition. Okay, so this is the list of polynomials in my list, such that the number of factors, the discriminant is 3. And that are unified at 2 primes. And I could, this is again an old example, I think this can be simplified. But So I want to select, so 3 primes is the most primes that can be ramified in these fields because they are subfields of these cyclotomy fields. So I'm selecting, so this is the list of all cubic fields ramified exactly at these primes. Okay. Yes. So this is the basic version, just giving the degree that you want, but sometimes you want to specify more precisely exactly one subgroup that you would like you would like a specific fixed field by a certain subgroup of the automorphism group of Q zeta n. So for that, you have to first compute. Well, this is the Ray class group for Q, but it's a very simple thing for the case of Q. It's Z mod Z n star. So you can compute the structure and generators of that with Z n star. It's the function. So you can do this. So you take G, this is the Z n star of n. So this gives you, yeah, here I showed you what is really inside. So this is the order. These are the cyclic factors. So it's Z mod 36 times Z mod 6 times Z mod 6. And these are generators. Okay, so it's these are the 3 generators corresponding to these 3 cyclic factors. Okay. And now we can describe a subgroup of this group by giving a matrix of generators expressed on this basis. So that's what I'm doing here. I'm writing a matrix. We call this description by rows. So first row, second row, third row. And then I'm asking for the HNF of that, but modulo 3. Because I will want subgroups of index 3. So I do want 3. So this constructs some specific subgroup of index 3. Will give me a matrix. Yeah. And now I can ask for not any cubic field, but the one that is fixed by precisely this subgroup that I took with Galois subcyclo. So this one here, we're not just specifying the degree, but the exact subgroup that we want, and it returns a cubic polynomial. And it's it's one from the list from before, but here we selected it like just the one we wanted. Yeah, so here I'm looking at the ramification that's ramified at these 3 primes. Yeah. Is this example clear? Yeah. Okay. Okay, so let's move on to bigger number fields than Q. So I will go by increasing complexity of define various extensions. So here, let's look at first the Hilbert class field. So this is the one that is attached to the class group. So I'm taking this imaginary quadratic field, and so I'm applying BNF in it to get the class group of that. Remember that .cyc gives us the cyclic factors of this class group. So the class group is what? Okay, what do you get? This clearly this is inconsistent. So 9. 9. Yes. Okay. So this is a typo. Sorry. Okay. I need to fix these slides. Okay. So the class group is Z mod 9 Z. And we can get a defining polynomial for that with the function BNR class field. So BNR, I'll explain a bit later where this is the prefix, and then class field, this is because we're computing a class field. So we apply this to our BNF, and it returns a polynomial like this, which, as you see, it's a polynomial of degree 9 with coefficients in this field. Okay, this A is you should think of it, this is a polynomial in A, but you should think of it modulo that one. So that's an element of this quadratic field. So we get it as a relative extension of the quadratic field. So you might not get the same result as this. The computation, there are some parts that are not deterministic. Maybe you won't get the same polynomial. Do you? Not the same. Yeah, that's not a surprise. Yeah, so conversely, if you start from an abelian extension, as I said before, it has to be coming from some ray class group. So you can do the reverse. You start from an abelian extension and you construct the class field theory data attached to it. So this is done with the function RNF conductor. So RNF stands for relative number field. So it's because you're considering relative extensions now. I mean, you have to say how this is an extension of the previous one. And so you give as an argument this pre-computed structure with class group and units and the relative polynomial defining your extension. And it gives you a bunch of data, gives you the smallest conductor for which it is a subfield of the class field, gives you, okay, this I will talk a bit about it later, and a certain subgroup. So in this case, we had done just the Hilbert class field, so we should just get the class group. And indeed, the conductor gives us, this is the identity matrix, so it means the trivial ideal, and empty, here the field is complex, totally complex anyway, so that cannot be. So, but this is the trivial modulus, so it means we're looking at the Hilbert. It's a subfield of the Hilbert class field, and the subgroup is given again as it's by its matrix. But I mean this just means the trivial group. I mean inside Z mod 9Z it's the trivial group. So yeah, so this is consistent with the fact that we constructed it as the Hilbert class field. If you prefer to have an absolute polynomial rather than a relative extension, you can pass a flag. I mean, you can also compute it as a posteriori if you prefer, but yeah, anyway, with a flag you can get the absolute polynomial instead. So now it's degree 18, but you don't get the map between the two fields. You forget that it was a relative extension. Okay, so now let's start doing examples where we have an actual conductor, so we'll have actual ray class fields. So these ray class groups are computed with the function BNR init. This R stands for ray. Okay, so you give it this BNF structure that has the class group and units, and you give it the modulus. Here I'm taking the simplest possible one. I'm just taking a modulus generated by an integer, but you can provide ideals and places as well. And then you can ask for the structure of this ray class group, so 722. And so you can see immediately that if I compute the full ray class field of that, it's going to be a very big field, yeah, because this is quite big extension. So it's often a better idea to try to get information about what the field that you wanted without actually computing it. That's the motto. Okay. So some of this information you can get with this BNR disk function. So you give it this BNR structure for the ray class group, and it will give you, well, the degree, the R1, so the signature, and the discriminants of the extension, but without computing it. Yeah. So yeah, we would get the field of degree 288, totally complex. Well, we start from a complex field anyway, and some big discriminants. Yeah. Okay. Is that okay for everyone? Is it also working for you? Yeah. So, so this one, it's a big field, but we still have some way of representing it in relatively compact form. So if you ask for the BNR class field to give you the field, what it will do is it's not going to give you like just this one enormous degree 288 polynomial. It's going to decompose it as a compositum of smaller fields. So what it does here, it gives it, okay, let's look at these outputs. So there's a degree 2 extension here. Then there's a degree 8 extension here, again as a relative polynomial. And then there's the degree 9 extension here. So you think of these 3 extensions. If you take the compositum of all of these, that's your class field. Okay, so it's in somewhat indirect description of this field, but compacting of that this is much faster to compute. If you absolutely want to have the single defining polynomial, you can get it. You pass a flag, and here I'm not displaying it because it's horrible. But if you can take a look and you'll get it. Is this working for you as well? Yeah? Okay, so very often you don't want the full ray class field, but you actually want a subgroup of the ray class field because you want some specific abelian extension from whatever property you wanted. So let's do an example here. So again, I'm initializing a ray class field, a ray class group. And let's say that I just want the 3 part of that, the elementary abelian 3 part of that. So then I pass this extra argument 3, meaning I just want the elementary 3 part of my extension, and then I will get these so 2 degree 3 polynomials here that generate my extension instead. And more generally, you could pass a matrix to try to describe the exact subgroup you're interested in. Yeah, okay, this is a bit what I was saying before. So can be very expensive to compute the actual field. So often it's a better idea to try to get some information beforehand. So we saw a bit of that with BNR disk. Another type of information you can get is splitting information from class field theory. So how do you do that? You want to know, so you want the Frobenius elements in your extension without actually computing the extension. And that's the same as the class of the prime in the ray class group. And so you can compute the class of ideals in the ray class group. That's done with the function BNR is principal. So same as yesterday, but in ray class groups instead of just class groups. Okay. So here I'm taking some ideal above 41, and I'm asking for its class in the ray class group. So argument is now this BNR representing this ray class group, the ideal. And then this 0 just means I don't want the generator part, I just want the discrete log. Okay. And so I get 0 as my discrete log, meaning this ideal is trivial in the ray class group. So it's generated by an element satisfying the congruence conditions. Okay. And so in terms of the extension, it means that this prime P41 is completely split in this degree extension that we have not constructed. Okay, this is good for everyone. Yeah. So this can be useful either to get information on an extension that you don't want to construct, or you can use this to pinpoint the exact extension that you want so that you don't have to construct a big one and then cut it off. You immediately construct the exact subgroup you're interested in. Or maybe you check whether it satisfies the property you wanted before starting a big computation that you might not need. Okay, so just to show how it's actually done in general, I'm doing an example where we have more general modulus as an actual matrix. So here, this is, instead of just generating it by an integer, I'm providing an actual general ideal in HNF form. We compute the cyclic factors. So of course, I'm never going to compute a field of that degree. So I just want some specific subgroup of index 9, let's say. So I'm giving this matrix. So this again describes one particular subgroup of my ray class group. And now I'm asking for the class field corresponding to that. And of course, it's not computing the big extension, it's just computing the one I'm interested in. So it gives me this degree 9 polynomial. Okay. Am I doing more examples? Yes, just with infinite place. Yeah. Is everyone okay with this? Is this getting a bit technical? Are you okay? Yes. It's almost break time. Should I just have a lot of? Yeah, we'll just finish this and then take a break. Okay, so yeah, I'm just showing you here how to specify the infinite places in your modules. Okay. So now I'm going to start with a real quadratic so that I have real places to work with. If I compute its class group, well, as often happens with real quadratic, it is trivial. And so look, am I doing here? Yeah, okay, this is the same. So I'm doing the ray class group with trivial modulus, but that's the same as the class group. It's trivial. I don't know why I put this slide. Anyway, but if I add the infinite places to my modulus, so I'm asking not about the ray class group, but the narrow class group, is what it's called in this case. I get Z mod 2Z, so has non-trivial narrow class group. So yeah, so in general, so how you specify a general modulus is you put a list with two elements. The first one is your ideal, the finite part of the modulus, and the second one is a sequence of zeros and ones of the same length as the number of real places, so R1, and you just put 0 if you don't want it in, and you put 1 if you want it in. Okay. And yeah, okay. So for instance, you could compute the class field here. I didn't do it. It's the same as before. And one last thing that is often useful to do, possibly before computing an extension, is the Galois action. If you started from a field which itself had automorphisms, then these automorphisms may act on the class group or on some ray class groups. And this gives you, again, information about the potential abelian extensions on top, because then the Galois group at the bottom could act on the Galois group at the top. So this is information you could want. And this is done with PNR Galois matrix. So that will compute the Galois action on the ray class groups. If it's well defined, it depends on the, so for it's only well defined for some modules. So, okay. Here's an example. We take some imaginary quadratic fields. It has these class groups. So again, Z mod 4, Z mod 2, Z mod 2. I'm initializing the ray class group, which is exactly the same as this class group, but I think PNR Galois matrix really wants a PNR, not a PNF. I'm initializing the Galois structure of this field. It's just quadratic, so the Galois group is just Z mod 2Z. And then I'm asking for how this, this complex conjugation in my quadratic field, how it acts on the class group. And this is done with this PNR Galois matrix. I give it the ray class group structure, the Galois structure, and gives me this matrix. So this is the matrix of the action on this. So it just, this is -1 in these 4 components. So it negates these components and it's, well, this one's just fixes them. This is the action. Okay. All right. Any questions? Let's stop here and have a break. Okay, so we resume at yeah. Let's take a half an hour break. Let's resume at 35 past. Yeah.
Hopefully she'll be there.
Okay. Yes. Is anyone staying in the room? Or, you're sorry. You're staying. Okay. Yeah, just so that we can leave computers and stuff. Yeah.
Okay, and you only require the first one is and you will still check. You will still check the property or all. You will still check. You will check that the automorphism preserve the transform. If you want to check and download it. And those, if you have the vectors, if you want to preserve a vector, because that's what you want to preserve a vector. Yeah. So what you do is that you add the form. So it's something like. V transpose V, something like that. This matrix. Okay. And so you see if your automorphism preserves this form, if only if yeah, you have phi of V equal to plus or minus V or something. Or and so what you do is that you ask Pleasant algorithm, not just for your lattice, but for lattice and this intersection of all. Complete the algorithm, the present is the souligné program. We automatically check. So we will only use this small vector for the first one. So first one is not defined positive. And so, but then it will still only keep the automorphisms that actually preserve also the second one. Okay, the two examples.
Right. Okay, thank you.
Because fundamentally, l'arch is that's functional algorithm, it's Schneider-6 algorithm. It's a random Schneider-6 algorithm.
Oh,
yes, so it's focused by organizer. And so you can always add conditions to reduce your culture. Yeah.
You just try pause, I don't know what that does, but. But it doesn't seem to have any impact pause. I don't know. Why not? Well, none of these appear seem to do anything.
I mean, is there a period and a point, mouse point? Or what? Do you even have a
Oh, you don't see, oh, I do here, I see, so you do, I see, so the mouse doesn't show the, it does show.
No.
I don't know why that is, because it
Oh,
shows
that
here,
doesn't
it shows,
doesn't concern me, no.
it shows here.
I see.
Oh, it does say recording, maybe that's a pause then.